Hi. In this third and last presentation belonging to the FSMD playlist, we will look at the VHDL description of the debouncer. After watching this presentation, I hope that you will be able to translate an ASMD chart into the corresponding VHDL description. You should keep this ASMD chart within sight during the remaining part of this presentation. You can do so by keeping the corresponding slide open in a new window besides the one that is showing this video, or alternatively just by keeping a printed version in front of you. Now, the book that we are following describes two implementations for this ASMD chart, one following an explicit data path method where the various sections are coded separately, and the other one following an implicit data path method using the usual two-segment coding style. Now, to keep this presentation short, we will only consider the implicit data path method, also because that's the coding style that we use regularly. But I leave it up to you as an exercise to go through the corresponding pages in the book and then to compare the two methods at the end. So let us start with the implicit data path method, where the architecture body begins by the usual signal declarations. Notice that we are using a constant declaration to define the number of bits of the down counter, and that's just to make it simpler to modify the code whenever we move to a different board that may use another clock speed. As an exercise, I leave it up to you to check if this calculation holds true for the case of the Nexus 3 board that we are using in this course. We also declare a user-defined data type to represent the 4 states of the finite state machine that makes up the control path of our FSMD. And of course declare the state register and state next signals that go along with it. And finally, we declare the various counter-related signals. So we are now ready to start coding the FSMD state and data register segment, which, as you might expect, follows the universal template that we have used several times before. So there's not much to say here. As you can see, we will reset these two structures if the asynchronous reset input is active, or otherwise just move them on to their next state. The second segment addresses the combinational logic blocks, and that's the segment that deserves most of our attention. So we start by focusing on the next state and data path logic for state 0, and so we will have 3 more slides similar to this one, corresponding to states weight 1, 1, and weight 0. Take notice that we start by defining the default signal values, which will apply if we don't say otherwise in each state code. And after this, what we have is just a case structure where we consider each state separately. You will notice that the VHDL description of the actions required in each state is simply a direct replica of the actions that are specified in the corresponding ASMD chart block. So in this case, we start by setting the dB level output to 0, since the state box in this state asserts no outputs. I'll leave this question here up to you. You should be able to answer it by now. Then we check if the switch is 1, and if so, we define the next state as wait 1, and we also initialize the counter to start decrementing once we move to the next state. You should also notice that there is no else part of this statement, and that's just because we have already defined that the default next state is the current state. Before moving on to state wait 1, please notice that the next state and data path process sensitivity list comprises 4 types of signals: the state register signals, that's the current state, the current value of the outputs of the counter, the switch input, and the next value of the counter. So for state wait 1, we again follow the ASMD chart directly, and the code that you see here is just a direct replica of the sequence of operations that are represented in the ASMD chart for this state. We set the dB level output to 0, check the value of the switch, and continue to decrement the counter if the switch remains at 1. And in that case, we will also check if the counter outputs have reached 0, and if so, define the next state as 1 and assert the dB tick output as indicated in the ASMD chart, of course. However, if the switch input is read as 0, this means that another glitch has been detected, and so we have to restart the process, and consequently the next state is defined as 0. By the way, you should be able to answer this question by now, but if you have any doubts, I can tell you that it is, of course, related to the default signal values that were defined in the previous slide. So to keep it short, I won't go through the same explanation here for state 1, since the code is again just a direct replica of the ASMD chart shown at the right for this state. But you can pause the video at this point and go through this correspondence by yourself. And likewise for the final slide, where you can find the code for state wait 0. Again, it's just a direct replica of the corresponding ASMD chart block shown on the right. So pause the video again at this point here for a minute and check the correspondence between the VHDL statements and the ASMD chart operations on the right. And that's it. Thank you for your attention.